Welcome back to the deep dive. Today, we are putting on our digital trench coats.
Yeah, I like that.
We're equipping ourselves with the finest instruments of network detective work. We are going deep, really deep into cloud networking.
And we're moving past the basics here. This isn't about just deploying infrastructure.
Oh, not at all. We're talking about forensic science, we're talking about financial auditing, and some really advanced troubleshooting in environments that are just, well, they're incredibly complex.
Think GKE clusters, peered VPCs,
Yeah.
layered firewalls,
Yeah.
the kind of setup where your traditional methods just completely fall apart.
Exactly. So this deep dive is really tailor-made for you, the network engineer, the security analyst, who's already operating at that intermediate or expert level.
Right, and if your go-to troubleshooting toolkit still kind of begins and ends with ping and trace route, you should prepare for a bit of a paradigm shift.
That's a good way to put it. We're going to show you how the cloud platform itself gives us this far superior, this native visibility right into the network fabric.
It's a kind of visibility that, honestly, often surpasses anything you can achieve from inside the virtual machine itself.
We've got a whole stack of sources today, and they really challenge some common assumptions about visibility, about cost control, and about network diagnostics. Our mission, our whole narrative, is structured around two big themes.
Two detective themes.
Exactly. First, we tackle what we're calling the CCTV camera. This is all about ensuring absolute forensic data integrity, especially when you're hunting for those elusive intermittent threats.
The ones that are designed to be missed.
And then second, we move to the simulation. We're going to learn how to analyze and troubleshoot connectivity in a total black box environment.
By mathematically modeling the network path without ever sending a single live packet.
It sounds like science fiction, but it's real.
It is. And that ability, the ability to treat the network as a software layer that you can analyze and simulate, that's the core concept of modern infrastructure detective work. We're really focusing on maximizing VPC flow log fidelity and then unlocking the power of reachability analysis.
All right, let's jump right in. We're going to start with a classic security headache, one that definitely keeps forensic teams up at night. Okay, so let's unpack this scenario. I want you to imagine the malicious ghost.
The ghost in the machine.
Literally. You're running a crucial application. This is your high-value production environment, and your security team flags something.
But it's not a big noisy alarm.
No, it's intermittent, low-volume communication, and it seems to be coming from your production front-end servers. We're talking about incredibly stealthy traffic.
Right, so maybe it's a command and control connection that only phones home once an hour.
Right.
Or it's exfiltrating data, but just, bit by bit.
Exactly. The point is, the traffic is specifically designed to be unreliable, to be transient. It just pops up, does its thing in a flash, and then it vanishes back into the noise.
And that is the quintessential needle in a haystack problem. But it's amplified by the sheer scale and complexity of a cloud network. Well, the traffic being intermittent means it's likely programmed with jitter, maybe some delay, or it only communicates in very specific time of day windows. It's doing all of this precisely to evade detection methods that rely on sustained volume or consistent patterns.
So the core question, the one we have to set up here, is critical. What specific configuration ensures we actually capture that intermittent traffic for forensic analysis? We can't afford to miss it.
You can't. And you have to assume the threat actor is intelligent.
Of course. They know we're locking things, so if they communicate only once every 5 minutes, or maybe only during periods when your traditional network telemetry might be under heavy load, a default setup or a reduced monitoring setup is just going to fail.
It guarantees the escape of the malicious ghost.
So we need non-negotiable coverage.
And this leads us straight into the deep technical mechanics of VPC flow logs. Specifically, the critical setting that determines forensic success or failure.
Which is the sample volume scale.
Exactly. Now, for our listeners who are deep in this domain, just a quick refresher. VPC flow logs capture a sampling of network flows. That's your 5-tuple data source IP, destination IP, source and destination ports, and the protocol.
And the really important part is where this happens.
Critically, yes. This capture happens at the hypervisor or the network fabric level. It happens before the traffic even hits the operating system of the VM.
And traditionally, a lot of administrators, they often use the default or a reduced sampling rate, maybe 0.5 or 0.8.
Right, and there's a reason for that.
Cost.
Cost and complexity. Logging everything generates massive amounts of data. And that means two things. A high storage bill, and a really high computational overhead for the security team that has to sift through all those logs.
But what happens when we rely on that lower setting, say, 0.5, when we're facing our malicious ghost?
That is the fatal trap for any forensic analysis. And we need to be crystal clear on what a 0.5 sample volume scale actually means.
It's not what most people think.
No. It does not mean the platform captures 50% of the network flows over time. It means that for every single individual network flow, which is often, the lifetime of a single connection tuple, the system makes an instantaneous, independent decision on whether or not to log it.
So a 0.5 scale means there's a 50% probability that any given flow will be captured.
A coin flip.
A coin flip. So if the malware is engineered to execute a single short-lived connection, like a rapid SYNAC handshake, a tiny encrypted payload, and then a FIN-RS to close it, that entire critical network connection has a 50% chance of being recorded.
And if you miss it, it's gone.
That evidence is gone forever. There's no getting it back.
And the risk here is cumulative. Let's say the threat actor initiates 3 different intermittent flows over the course of an hour. If we're running at 50% sampling,
the probability of missing at least one of those critical data points just jumps significantly.
Exactly. For forensics, this kind of probabilistic approach is completely unacceptable. We aren't looking for a general trend in traffic. We are looking for a singular event, an atomic action of compromise.
One packet, one flow.
If the platform skips that single flow, that one piece of evidence, the target IP, the timestamp, the port, it's irrecoverable.
Okay, so let me challenge that for a second. In a massive production environment, one with petabytes of daily traffic, moving to a 1.0 sample rate that could turn an already expensive logging bill into something potentially crippling, how do you justify that astronomical overhead to the CFO just to hunt for a ghost?
That is a fair and a completely necessary challenge. And the justification is that the cost of forensic certainty in this specific case is dwarfed by the cost of a sustained, undetected breach.
So it's risk management.
It's pure risk management. We're talking about highly sensitive production servers. So the first step is to recognize that the 1.0 sample volume isn't necessarily a permanent state. It is a forensic integrity setting. You enable it for the duration of the investigation to gather the evidence you need, and then you can scale it back down.
Okay, that makes sense. It's a temporary measure for an active incident.
But let's address the scale challenge directly because it's a real one. When you move to 1.0, you absolutely must have an efficient log consumption strategy. You can't just afford to route 100% of your VPC flow data into your standard cloud logging sinks if the environment is massive. It won't work.
So what's the architectural solution?
The architectural solution to handle that influx of data is to shift the sync target. You move it away from the standard interactive log viewer, and you push the raw flow logs directly into high-scale, low-cost storage. Think BigQuery or cloud storage.
Ah, okay. So we're moving from interactive, near real-time logging to a massive data lake for archival and batch analysis.
Precisely. BigQuery lets your security analyst run these incredibly complex, incredibly fast queries across the entire data set. You can filter out all the known internal traffic, look for flows going to specific external IPs, or isolate traffic based on the suspected protocol.
Which significantly reduces that sifting overhead you mentioned.
Exactly. You're shifting the computational load from the logging service to the query engine, but you maintain the integrity of the raw data capture. You lose nothing.
So the analogy really holds up. If you only record 30 seconds out of every minute, you are almost certainly going to miss the burglar if they're fast.
For forensics, you need that camera recording 247.
Which translates to the 1.0 100% sample volume scale. This ensures that every single flow that passes through those production subnets is captured. No exceptions.
And that leads us to the conclusion for this whole scenario. The correct action is enabling VPC flow logs on the production environment subnets with the sample volume scale of 1.0.
And we'd completely ignore the options suggesting lower sampling rates or, making changes in a test environment first.
Because the malicious activity is current and it's in production. Any option with a 0.5 sample volume scale is just fundamentally flawed for capturing intermittent, evasive traffic. It's the wrong tool for the job.
That's a powerful lesson.
Yeah.
Prioritizing integrity over cost optimization when the stakes are at their highest. Now, let's transition from that kind of comprehensive capture to something more Surgical.
Surgical logging, I like that.
Right. VPC flow logs at 1.0 are fantastic for that broad forensic capture, but sometimes you don't need to log every single flow moving across a massive subnet. Sometimes you just need to log specific hits on a very, very permissive rule.
And this changes the optimization goal completely. We're moving away from forensic integrity and towards operational efficiency.
What's fascinating here is how we're measuring that efficiency. The constraint is that we need to log every IP address accessing a specific API, but we have to do it using the fewest number of steps possible.
So we need to find the most efficient logging mechanism that's tied directly to the access decision point.
Okay, let's set the scene for this one. You're managing a custom HTTP server API. It's being accessed via an internal TCP/UDP load balancer.
And crucially, there's a very permissive firewall rule currently allowing access to the API port from 0.0.0.00.
It's wide open. Maybe it's temporary, maybe it's for a test, but the point is you need an audit trail of who is actually using that permissive access right now.
Okay, so we have several options on the table. They're all viable, but most of them are inefficient for this specific goal.
For example, we could just enable general VPC flow logs on the entire subnet.
Right, that's one option. Or we could go the other way and install the ops agent on the compute engine instances themselves to capture application-level HTTP access logs.
But both of those introduce a lot of unnecessary overhead, so let's break that down. Why is VPC flow logging on the whole subnet less efficient in this specific audit scenario?
Because it captures way too much noise. If that subnet also handles traffic for 5 other services, the flow logs are going to capture traffic for all 5 of them, plus all the internal health checks, monitoring traffic, system flows, everything.
So the forensic analyst then has to build these really complex filters just to isolate the traffic hitting the one specific port and protocol that permissive rule targets.
It works, eventually, but it's not surgical. It's a blunt instrument.
And installing an ops agent, that just sounds like management sprawl to me.
It absolutely is. Installing the ops agent means you have to manage the agent lifecycle, you have to ensure it's running correctly on the OS, you have to configure all the necessary log syncs, you have to deal with potential resource consumption on the VM itself.
And you might even need additional firewall egress rules just for the agent to phone home.
Right. This is a significant amount of operational overhead just to capture a simple network access audit trail. Remember, we're looking for network-level data tied to the access attempt, not the application behavior inside the VM.
And I think we can dismiss packet mirroring immediately, right? That seems like extreme overkill.
Oh, completely. That's reserved for deep packet inspection, decryption, high-fidelity IDS systems. It's like using a sledgehammer to crack a nut.
So the simplest, most direct, and therefore most efficient action is to leverage the platform component that is already performing the access control decision.
The firewall rule itself.
The correct solution is to just enable logging on the firewall rule.
It's truly surgical logging. The firewall rule is the ultimate choke point. It's the gatekeeper that evaluates every single packet against that 0.0.0.000 source and the destination port before the traffic ever even reaches the VM.
And what do you get when you turn that on?
When you enable logging on the rule, the platform captures this rich metadata about every single packet hit against that specific rule. This metadata includes the source IP, the destination IP, the protocol, the port, the time, and the explicit action that was taken, allow or DD&Y.
So you get clean, concise, network-level data that is directly relevant to your audit requirement.
And it generates far less log volume than subnet-wide flow logs, and it requires zero management or overhead on the compute engine instances themselves. It really embodies this idea that efficiency in the cloud means using the native features of the resource you're actually auditing.
All right, let's shift our focus now. We're moving from security forensics to financial forensics.
Following the money.
Exactly. The network architecture decisions we make can often hide these significant accumulating costs, and network cost optimization is often a hidden challenge, especially when you're managing dynamic, complex deployments like GKE.
It's a huge one.
So let's look at a scenario. We have a GKE cluster backend. It's serving HTTP requests for a popular mobile game, and the stated goal is purely to reduce network cost. Nothing else.
This is such a critical lesson because it forces a cognitive separation between what we think of as architectural best practices and what are actually financial best practices.
What do you mean by that?
I mean, many standard architectural choices, like using a private cluster or a robust load balancer, are excellent for security, for resilience, for performance. But they're often neutral or even detrimental to reducing your network data transfer costs. We have to follow the money trail.
Okay, so let's dismantle some of those false solutions. These are things that are architecturally sound, but financially irrelevant to the goal of reducing data egress cost.
Let's do it.
Why do options like, say, configuring a shared VPC host project or using a private cluster or setting up an HTTP load balancer as ingress, why do those not inherently guarantee reduced cost?
Okay, let's start with shared VPC. Configuring a shared VPC host project is fundamentally a security and centralized management mechanism. It lets different service projects share a single, defined VPC network and centralize resources like firewall rules.
So it improves governance and operational efficiency.
Exactly. But it does not fundamentally change the network data transfer pricing model once that traffic exits the VPC boundary to go to the internet.
Yeah.
It's an organizational choice, not a cost reduction lever.
Okay. What about a private cluster? That's all about isolation.
Precisely. A private cluster ensures your cluster nodes and the API server only use internal IP addresses. This is a powerful security posture. It significantly reduces your external attack surface, but the traffic flowing out of the cluster via your services, the data egress charges for the mobile games users, that still follows the exact same data transfer pricing tables. You haven't lowered the cost per gigabyte, you've only improved the isolation. If your traffic volumes stay high, your cost structure stays unchanged.
And the load balancer, we know that enhances performance and scaling.
Oh, right. Configuring an HTTP load balancer as ingress is a performance and service delivery choice. It gives you features like global distribution, intelligent traffic steering, SSL termination. It optimizes the experience for your users, it distributes load efficiently, and it increases resilience.
But again,
the load balancer is a service that sits on top of the network tier. It's either neutral or slightly additive to the cost compared to the fundamental data transfer charges associated with the underlying network tiers.
so if we strip away all the security, scaling, and management concerns, all those core architectural choices, we're left with one decisive lever for reducing network cost.
The true solution is to tackle the pricing structure head-on. You have to configure your network services on the standard tier.
Okay, this forces us, the expert listener, to deeply understand a fundamental high-level distinction between premium tier and standard tier and how that directly impacts the bill. So if we connect this to the bigger picture, what's the infrastructure difference that justifies that price differential?
It really just boils down to the route the traffic takes. The premium tier is optimized for global low-latency performance. When you select premium, the platform utilizes its immense proprietary global backbone network, a private fiber optic infrastructure that spans the world.
So your traffic gets on a private highway.
A private superhighway.
Yeah.
Your traffic enters that private network as close to the user as possible at the nearest point of presence, or POP, and it travels across the platform's optimized low-latency backbone for as long as possible before it finally reaches the application region.
And because you're using this ultra-high-performance, privately managed, heavily redundant global infrastructure for the long haul, the cost is naturally higher.
Of course. It's the highest quality, lowest latency route available. You're paying for global reliability and speed, no matter where your users are relative to your application.
Okay, so that's premium. Now, what about standard tier?
The standard tier is explicitly optimized for regional routing and cost reduction. When you use standard tier, the traffic travels over the public internet and standard ISP pathways for the longest portion of its journey.
So it's on public roads for most of the trip.
Exactly. The platform's proprietary backbone is only utilized within the region that's hosting the application. Since the service leverages standard carrier infrastructure outside of the platform's high-cost private backbone for that long-haul travel, the data transfer cost is significantly lower.
The trade-off is clear. You're sacrificing global, guaranteed low latency for cost savings, and you're relying on the performance of the general internet and peering agreements.
And if your application footprint and your user base are highly regionalized, that latency trade-off might be completely negligible, but the financial savings are substantial.
For a huge mobile game, even a fraction of a cent saved per gigabyte of egress data.
It quickly scales into millions saved per year. Therefore, if the primary goal is purely cost reduction and your regional performance requirements can tolerate slightly higher, public internet latency switching from premium to standard tier is the single most direct financial control you possess.
Let's apply that financial detective work to a really exquisitely constrained scenario, because I think it highlights why this alignment is so crucial.
And it helps illustrate that standard isn't inherently worse, it's just situationally specific.
Exactly. So our scenario involves a front-end tier and Nginx servers running in a managed instance group fronted by an Envoy HTTPS load balancer. All of it is deployed entirely within the Europe West 2 region, which is London.
And here's the critical constraint. This service serves only users based in the United Kingdom.
And here's where it gets really interesting. Because this is the ideal case for cost optimization. We have a perfect regional match. The application footprint is local. The user base is local.
There is literally zero technical or performance benefit to involving the massive overhead of the global routing infrastructure or the premium tier.
None at all. The optimization goal is explicit. Choose the most cost-effective network tier and load balancing configuration that still meets the regional performance requirements.
And since all the users are geographically co-located with the service, the traffic flow is almost entirely regional.
So if we were on premium tier here, our traffic would hit a POP, enter that private backbone, travel internally for just a short hop to the London region, and then exit. We'd be paying the premium rate for a global guarantee we don't need.
Precisely. And if you use a global load balancer, which typically works best with premium tier, you're also maintaining state and configuration across a global control plane completely unnecessarily. The application just doesn't need global distribution.
So the definitive choices.
Standard tier with a regional load balancer.
Okay, so why does specifying the regional load balancer matter here, even if the tier is set to standard? Why not just a global standard tier setup?
It's about minimizing the control plane complexity and maximizing that regional efficiency. A regional load balancer operates only within that specific region, Europe West 2. This simplifies your operational management, it ensures all the traffic processing stays local, and most importantly, it eliminates any potential complexity or hidden charges that might be associated with traffic accidentally being routed through global services.
So it's a perfect pairing.
It's the perfect harmony of architecture and finance. The standard tier dictates the data transfer pricing, and the regional load balancer ensures the architecture is tightly coupled to that regional constraint. It delivers the lowest possible data transfer cost, optimized for that UK-only user base.
It's a superb illustration that the most complex globally distributed architecture is very often the most expensive one. And sometimes embracing simplicity and regional constraints is the truly expert move.
All right, now for our final act of detective work. We are tackling the black box.
My favorite. This is a situation where we have to diagnose a critical network failure, but we are explicitly forbidden from using our traditional OS-level tools. This is where network analysis becomes pure configuration science.
And this scenario is becoming more and more common, especially in highly regulated or security-conscious environments, particularly those running complex platforms like GKE.
The security posture dictates a hard constraint. The operations engineer does not have execute access to the workloads or nodes.
That means no SSH, no ability to run ping, no traceroute, no permission to deploy debug containers into the cluster, nothing.
That is just paralyzing for a traditional network engineer. I mean, if I can't send a batch and see where it dies, how can I possibly diagnose the failure?
And that is the crux of the problem definition. You're configuring connectivity across two GKE clusters in different VPCs, cluster A and cluster B. They can't communicate.
And you suspect a network configuration issue, a missing firewall role, an incorrect route, maybe a faulty peering configuration. The challenge is, we need to identify the exact layer at which the connectivity is broken without sending a live packet or logging into a machine.
So we can't test the network dynamically. We need a tool that can essentially read the mind of the network fabric statically.
Which raises that important question. How do we analyze something we literally can't touch?
Well, let's first truly understand why the old methods fail under this no execute access constraint. Running traceroute from a debug container is prohibited. Checking routes manually via an OS-level toolbox is prohibited. Even running a simple TCP dump on a node is prohibited.
And critically, even if we were allowed to enable VPC flow logs, there's still not enough here.
They're insufficient. Flow logs are reactive. They audit traffic after it has already happened. They might tell you a packet was dropped, but they don't give you the deterministic configuration-specific why in real time. We need a predictive analytical tool that isolates the configuration bug before any traffic is even generated.
We need something that can map the entire network configuration state and just calculate the outcome of a theoretical packet flow.
Exactly. And the modern cloud solution leverages this native platform intelligence built into the Network Intelligence Center. You use Network Connectivity Center to perform a connectivity test.
Okay, let's do the deep dive into reachability analysis. And we should probably clarify the nomenclature first, because some of our sources, they seem to use Network Connectivity Center and Network Intelligence Center a bit interchangeably.
That's a crucial distinction to make. The Network Intelligence Center is the umbrella term for a whole suite of diagnostic, monitoring, and verification tools that the platform provides.
And the connectivity test is one of those tools.
Right. The connectivity test feature, which performs the actual reachability analysis, is one of its most powerful components. The Network Connectivity Center, on the other hand, is generally a hub focused on connecting hybrid and multi-cloud environments. Things like managing VPNs, interconnects, router appliances.
Okay, understood. So while the test might involve elements managed by the connectivity center, the analysis engine itself sits within the network intelligence tools.
Precisely.
So now let's get into the mechanics of the connectivity test. This is the radical departure from traditional networking.
It absolutely is. It is a purely mathematical simulation of the network path. It's based entirely on the defined configuration state of the virtual network fabric. It is not a live packet transmission.
So think of it as a virtual simulator.
That's a great way to put it. It constructs a theoretical packet, say TCP from IPA port X to IPB port Y, and then it runs that theoretical packet through the entire configuration hierarchy of the platform.
So the platform treats the entire VPC, including all the routing tables, the peering configuration, the firewall rules, network tags, implicit policies. It treats it all as a giant equation to be solved.
That is the perfect analogy.
Right.
It analyzes all the configured network components in the exact hard-coded order that they would be processed by the underlying hypervisor. And this order is critical.
So what's the order?
First, route evaluation. Does a route even exist for the destination IP? Is it a default route, a custom route, a peering route? Then second, firewall rules, egress and ingress. Is the traffic explicitly or implicitly denied or allowed by any firewall rule? It checks the priority, the direction, everything.
Okay.
Third, VPC peering or VPN status. Is the peering connection active and correctly configured? Is the VPN tunnel actually up and routing traffic? And then finally, things like IP address configuration. For GKE, this is IP aliasing. Is the source or destination IP correctly mapped to the virtual network interface? It checks everything.
The value proposition here is just immense, especially given our security constraint. We can't log into the machine. This tool operates at layer 0, the infrastructure configuration layer, entirely bypassing the workload and the OS.
And it predicts the fate of the packet with 100% certainty based on the current configuration. You don't get a vague request and timed out error. You get a definitive configuration failure report.
Instead of seeing a connection timeout, the connectivity test will return a result saying exactly where the packet would be dropped and which configuration element is responsible.
Give me a real-world example of the output we would see from this.
Okay. A traditional ping failure just gives you latency or a drop. A reachability analysis failure might state, and this is almost a direct quote, packet dropped. Ingress firewall rule gut cluster, a policy tag deny with priority 1000 blocked TCP on destination 443.
It's that specific.
It's that specific. Or if it's a routing issue, it might say, packet dropped. No route defined for destination subnet 10.42.0.016 via VPC peering, cluster B peering.
That shifts the entire troubleshooting focus. You move immediately from, is the process listening or is the OS firewall configured correctly, to why did the platform configuration drop this packet before it even reached the destination host?
It identifies the failure at the configuration layer immediately, regardless of the workload state or our limited access rights.
And this is particularly powerful in GKE environments. GKE networking relies so heavily on concepts like IP aliasing, secondary IP ranges, internal load balancing, all things that often confuse traditional diagnostics.
A simple ping often just tests the physical node interface, not the complex network fabric that handles pod-to-pod or cluster-to-cluster communication.
And reachability analysis just cuts through all of that complexity to test the true network path as it's defined by the platform's control plane.
So the core takeaway here is that modern cloud troubleshooting lets us debug the fabric itself. We're moving from this cumbersome trial and error process of OS-level diagnostics to
deterministic, predictive, platform-level analysis.
It removes the black box element. You're no longer guessing what the network is doing internally, and the platform, which builds and manages that network, is giving you its internal logic, its decision tree in explicit, actionable language.
And this allows a network engineer to diagnose and fix configuration errors in minutes, even with zero SSH access to the underlying computing resource.
It's the ultimate tool for the modern cloud detective who can't contaminate the crime scene by setting foot inside the host. So this deep dive has really clearly established that becoming a truly effective network detective in the cloud means moving beyond the familiar OS-level utilities.
It really does. It means mastering the platform's native tools for forensic integrity, for financial auditing, and for configuration simulation.
Let's quickly consolidate the three crucial advanced concepts we covered today for you, the expert listener.
Okay. First, when you're dealing with highly sensitive or intermittent malicious activity, that malicious ghost forensic integrity demands a 1.0 sample volume in your VPC flow logs. And you have to pair that with a scalable logging sync like BigQuery to ensure you capture every single piece of potential evidence.
Second, financial detective work is paramount. Cost optimization requires you to align your architecture with the platform's pricing tiers. For purely regional deployments serving regional users, the standard tier, combined with regional load balancing, is the mathematically and financially optimal choice.
Using premium tier in that scenario is just paying extra for a global guarantee that you do not need.
And third, cloud troubleshooting demands a shift from reactive monitoring to predictive simulation. We have to rely on reachability analysis, the connectivity test, to simulate potential network paths and diagnose configuration failures instantly.
Which enables us to debug these complex environments like GKE without ever needing execute access to the underlying nodes.
The ability to model the network mathematically, to treat the entire fabric as a debuggable piece of software, is fundamentally transforming how infrastructure detective work is done. It's moving network analysis from guesswork and latency checks to deterministic configuration analysis.
And that leads us to our final provocative thought for you, the listener, as you continue to build and secure these sophisticated architectures. We demonstrated how platform tools effectively replace OS-level troubleshooting, like SSH and ping.
So think about the security operations you handle every day. What traditional security function that's currently done inside the VM, like the installation of a specific host-level logging agent, or vulnerability scanning that relies on OS libraries, what's next?
What's the next thing that's going to be absorbed and solved more efficiently and natively by a core control plane cloud service? How much longer until the platform security intelligence completely obviates the need for traditional host-level security management tools?
Something to mull over as the cloud continues to abstract away the operating system. Thank you for joining us for the deep dive. We'll catch you next time.